Hey everybody, we are live and in stereo. So today we are gonna try our best to cover 95% of Hess cycle. 5% is still gonna be left because I want to teach that in the next live class, and obviously that's gonna be with the live batch. But I want to finish off 95% of Hess cycle today. We've already covered 70% till yesterday. 70% has already been covered in the last two classes. We just have to cover 20 more percent and then 20-25%, and then just 5% is going to be left for the next class, right? Because I want to keep the next class short since we'll be starting off with equilibria, right? So effectively what we were talking about last time was that Hess's law was a very creative way. It was a very creative way to figure out enthalpy changes which we could not practically measure, right? We could not practically perform those experiments, and we had so many examples in the last class that there are experiments, for example, the decomposition of calcium carbonate into calcium oxide and carbon dioxide. We couldn't directly measure the enthalpy change for this reaction, and that is where Hess law came into play, because Hess literally said that the enthalpy change of any chemical reaction is independent of the route that it takes, provided that the initial and final conditions remain the same. So you can have another route for this calcium carbonate and then end up in calcium oxide and carbon dioxide, and that route would effectively be measurable. But this particular route was not measurable, and there are reasons for it which you don't need to know. For example, carbon burning in oxygen to give you carbon monoxide. We could not practically, in no lab on the face of planet Earth, can you practically figure out directly the enthalpy change of carbon monoxide. No, you can't do that, right? But you can actually figure it out through different creative ways using the Hess's law or the Hess cycle. And we've already studied how we calculate this stuff in the last class, right? And the reason why you can't do it directly is because whenever carbon burns in limited oxygen, it does form carbon monoxide, but the reality is also that even if there's limited oxygen, some carbon dioxide also forms. Always some carbon dioxide still forms even in limited oxygen. But this, my dear fellas, is an unavoidable reaction. It's unavoidable. You can't do anything about it. So you can't directly figure the enthalpy change when carbon burns in limited oxygen to give you carbon monoxide, because this fella also forms. This pariah, Abdullah mein shadi diwana, whatever, this also forms, right? And you can't stop this. So we figured out creative ways to do it, and we did a lot of examples in the last class. Now today what I want to do is I want to recap the bit which is largely focused on your in your syllabus, which is the enthalpy changes of formation, right? So we knew that in Hess cycle, if the enthalpy change of formation data for both reactants and products are given to me, is given to me, we can actually calculate what? We can actually calculate the enthalpy change of that particular reaction. We can calculate the enthalpy change of reactants going into products with the help of a shortcut, because we know that if we want to figure out the enthalpy change of this particular reaction of reactants reacting together and forming products, and we have enthalpy change of formation data for all the reactants, for all the products, it's a pretty easy way, because we know that enthalpy change of formation, for example, I want to say, hey, what's the enthalpy change? Can you guys write the enthalpy change of formation for equation for C6H12O6? We can absolutely do that, because it's for 1 mole of this substance forming from its elements in its standard state. So this is graphite, this is then hydrogen, and this is then oxygen, and you have 6 carbons here, you have 6 hydrogens here, and you have 3 oxygens here, and this is in fact the enthalpy change of formation reaction for equation for the formation of glucose, right? So it's enthalpy change of formation of glucose under standard conditions, with all the reactants, with all the elements in its standard state, and all of that good stuff we studied in the last class. Great, right? But we also know that if I have these elements with me, if I have formation data of C6H12O6, I can just literally calculate the enthalpy changes of formation from my elements, right? So I'll have elements, sir. I'll have the formation data. Hey, this much energy is required to make this product. This much energy is required to make this product. This much energy enthalpy change is to make this reactant. This is the enthalpy change to make this reactant, and so on and so forth. So this was the trick that we used, right? And I'll give you one recap example. For example, I have N2 plus N2H4 plus O2, and that this enthalpy change I want to figure out, and I have nitrogen plus H2O forming, right? This is what I want to figure out, and I'm going to give you formation data. So whenever formation data is given to you in the exam, he'll give you the formation data of the reactants, and the examiner will also give you the formation data of products, right? And you can easily figure it out. You don't even have to write the elements. You don't have to write the elements. You can just write the word elements right here, because we know that formation data is for 1 mole of a substance forming, 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 right? So these elements, no matter how many moles of these elements is used, it is irrelevant for all of us, right? So the enthalpy change of formation data for this particular reactant is, let's suppose, like, and let's also balance this stuff, you know, there's a 2 here. So for this was what? It was plus 51, if I'm not wrong, kilojoule per mole. And this, for H2O liquid, it's about minus 286 kilojoule per mole, right? And the way we calculated this was pretty simple. We said, hey sirree, let's draw our 3-box diagram. Let's draw our 3-box diagram, and I'm going to put the most populated equation in this diagram, which is this fella right here. This is the unknown, and this is the most populated equation as well. So most populated means the most reactants plus products, right? So N2H4 plus O2 gives me what? N2 plus 2H2O, and these are my elements, right? Now you may be wondering, sir, the examiner has not given me the formation data of this element right here. The examiner has not given me the formation data of nitrogen right here. Sir, we know the formation data, the enthalpy change of formation for any element is 0. And I've gone over a lot of detail in the last couple of classes that it's a null reaction, and all the explanation has already been given to you. I'm just recapping stuff. But the enthalpy change of formation of N2H4 is given. That's plus 51 right here. And for H2O, remember, enthalpy change is for 1 mole of that substance forming, right? So for 1 mole of H2O, this much energy is given out. So this is the enthalpy change, sorry. So it's minus 286, but this is for 1 H2O, 1 mole of H2O. How many moles of H2O do I have? 2, right? So I have 2 moles of H2O. And this, my dear fellas, is X. Now I can use my direct and indirect route. I can say, hey, this is the indirect route and this is the direct route. So it's going to be plus 51 plus 0 plus X equals minus 286 into 2, right? See, the indirect route equals the direct route. And so what do I get? X equals minus 286 into 2. That gives me minus 572, and this minus 51. What do we get? Enthalpy change of this reaction is what? Minus 623 kilojoule per mole. And this is what we covered in the last class, and we did a lot more examples in the last class. I just wanted to recap this. And the reason why I recapped this is because this was the formation shortcut. So if you are given formation data, and frankly speaking, let me tell you guys something, in the entire world, in our world, whenever you want to figure out the enthalpy change of reaction, this formation data is readily available for us. So largely speaking, whenever we want to figure out any enthalpy change, we do it with formation data, because it's a piece of cake. With formation data given to me, it's just a piece of cake to calculate the enthalpy change of any reaction. And this is how we practically even do it in big sophisticated labs, right? Sir, my college tutor glossed over all of Hess cycle in like 20 minutes. This is so crazy. I know. Sir, we will miss you. Abdul Muiz, I will also miss you. I'm not dying. Please don't kill me. Now, the second shortcut to it is, that we need to study is if you have reactants and if you have products, right? So again, here reactants are going to go into products. Now, sir, what in the hell are you saying? We had reactants and products here as well. You were saying reactants go into products, and I'm given formation data, and we were using formation data to our advantage. What's the difference between this and this? It's the same thing, isn't it? No, it's not. Why? Because reactants and products are given, but the data of formation is not given to us. Then which data is given to us? If the data of formation is not given to us, then which data is given to us? It's the data of combustion. The data of combustion, right? Sir, is the data of combustion available for reactants and products both? The answer is yes. That's where you can use this second trick. And this is largely used in organic chemistry and when you're dealing with organic molecules. Because we realize that organic molecules are largely combustible. The reactants can also undergo combustion. The products can also undergo combustion, right? So if we are given enthalpy change for combustion for reactants and products, provided they both can be combusted, we can literally figure out the enthalpy change of the reaction. Sir, how do we do this? Please tell us. Oh my God. Let me tell you. Let's understand it through an example. You have C3H6. This is effectively like propene. Nobody cares what it is for now. And this is H2 gas. And it gives me C3H8. And this, I don't know. I don't know the enthalpy change right here. Nah. I don't know. But the examiner will give me the enthalpy change of combustion data for all the reactants and all the products. Sir, how can the examiner give you the combustion data for all the reactants and all the products? He can give me the combustion data for all the reactants and all the products because the examiner knows that all the reactants and the products are combustible. C3H6 is a fuel, it can undergo combustion. H2 can undergo combustion. C3H8 can undergo combustion. This can undergo combustion, this can undergo combustion, this can undergo combustion, and they will form something known as combustion products. It can be carbon dioxide, in this case it's carbon dioxide and H2O, in this case it's H2O, in this case it's carbon dioxide and H2O. But do we really care how many moles of combustion products are forming? Do we really care how many moles of carbon dioxide are forming? How many moles of H2O are forming? No. Why? Why don't we care? Because combustion data is for 1 mole of the substance which is burning. So the data is given from this perspective, not this perspective. Please understand. That's why we don't care how many moles of carbon dioxide, how many moles of H2O, or what exactly is forming. Nah, we don't care. We just care, hey, if combustion data is given to me, combustion data, you can even write the equations for yourself. C3, what's the combustion equation for C3H6? Is C3H6 plus O2 gives me carbon dioxide and water, and it's just a waste of time. Similarly, H2 plus O2 gives me H2O. That's the combustion equation for this. What is the combustion equation for C3H8? C3H8 plus O2 gives me carbon dioxide and water, and make sure that this is 1, this is 1, this is 1. And how do I make this 1? Balance the entire equation. So this is 3 moles here, this is 3 moles here, 3 and 3 is 6, great stuff, and then it's 3 times 2 gives me 6, 6 plus 3 is 9, so this would be 9 over 2. Do I really care? No, I don't. This is half. This is how many? 3 moles here, and like 4 would come here, because see, you have 8 hydrogens here, 4 times 2, 8, right? I'm not here to teach you balancing. Nah. 3 2s are 6, 6 plus 4 is 10, so I'd put a 5 here. Nobody really cares, because the data that has been given to me is the combustion data, and it's always from this perspective. Right here. So it's always from the perspective of the fuel which is being burnt. So I couldn't care less about how many moles of carbon dioxide are forming. Is carbon dioxide only forming, or is H2O also forming? Is carbon dioxide H2O both forming? How many moles are forming? Nah. We don't care about that stuff. And that's why it becomes pretty simple for us. That's the technique that we use. So we say, hey, reactants go into products, and if they are both combustible, if they both can undergo combustion, if reactants and products can both undergo combustion, you're going to end up with combustion products. How? By reactants by using the enthalpy change of combustion for the reactants, for each reactant, by using the enthalpy change of combustion for each product, and that's it. Literally, this is how the diagram would change. See, formation is totally opposite. You are forming them, and you couldn't care less about how many moles are forming this, because formation data is given from the perspective of what is being formed. So the formation data of H2O was given for 1 mole of H2O forms, not how many moles of elements were required to make 1 mole of H2O. Nah, it's for how 1 mole of H2O forming. If you had 2, you just multiplied it by 2. Similarly here, I couldn't care less about how many combustion, how many moles of carbon dioxide are forming, how many moles of H2O are forming. Is H2O only formed? Nah, I don't care. I only care about how many moles of reactants are forming this, because combustion data is for 1 mole of that substance, for 1 mole of this, for 1 mole of this, right? And in this case, we only have 1 mole, 1 mole, and 1 mole. So it's pretty basic, right? So let's do it. What am I going to do? I'm going to write my equation. I'm going to write the equation. What is that equation given to me? C3H6 plus H2. So C3H6, oh, sorry for my pathetic writing, C3H6 plus H2, and that's X. I don't know. Oh, why am I not drawing my boxes? First, let me draw the box. I totally forgot that I have this thing installed, right? So C3H6 plus H2 going into C3H8. I am gonna find this, and I'm given enthalpy change of combustion. For what? I'm given enthalpy change of combustion data for C3H6. Let's suppose that's like about minus 2509 kilojoule per mole. This fella is like minus 286 kilojoule per mole, and this fella right here is about minus 2220 kilojoule per mole, right? Let's do this now. Let's do this. Let's just do this. So these are combustion products. I don't even have to write carbon dioxide, water, no, I don't, because I'm just want to combust. I just want to combust this. So C3H6, what's the combustion data for it? I'm going to draw a straight arrow because Sir Suleiman, please, you've been drawing straight arrows. Draw a straight arrow. Okay. C3H6 combustion data minus 2509. Minus 2509. H2 combustion data. Please be very mindful of the idea that if H2 was gonna form here, let's suppose H2 was forming here, right? Just assuming, what would be the enthalpy change of formation for H2? That's 0, because formation for data for element is 0, 0, 0, 0, right? It's 0. But combustion for H2 is there. H2 is gonna undergo combustion, and it's gonna form what? It's gonna form H2O, right? I don't care. Yes, you are right. The equations are not necessary, but you should know how to write combustion in standard enthalpy change of combustion equations. I've taught this in the first class, not the second, the first class. But these equations are not needed. You are right. They are not needed. But I'll tell you, you need to have an idea of how to write these equations or how they look like, because sometimes the examiner will not give you questions like this. He's going to write equations for you, and if you don't know if the equation is about enthalpy change of combustion or formation, you're cooked, right? So that's the idea. Here, H2 undergoing combustion, that's minus 286, and similarly products undergoing combustion. And see, this can only work if reactants and products alike can undergo combustion, right? So for products is minus 220 kilojoules. And then again, you can use anything, right? So you can say, hey, the direct root, or let's do it like this, the direct root equals the indirect root, right here. See? Or the direct root equals the indirect root. It doesn't really matter what you call direct, what you call indirect, but the direct root equals the indirect root, right? So x, where is this? This is my indirect root. X plus minus 220 equals to this plus this, right? So x plus minus 2220. Please, you need to add a positive sign. Plus is very important, right? It's just the law of heat summation. It's summation, not subtraction, right? And then that would be equal to minus 286. I'll put it in brackets, plus minus 2509. What do we get, sir? Hanji. Yes, Maz, if you've not seen your past paper, they do ask you what is formation and what not. They do ask everything. Sir, how long is today's class? Today's class is going to be... Sir, I showed my teacher the three equations. The three equations trick that you showed us, and if our teacher said that what if you don't have equations? Can we have such questions where equations are not given? Here you go. Come on, we've been doing this since yesterday. Equations aren't given. Right here, formation, combustion. Equations aren't given. I'm just writing the equations for you so that you guys know what formation and combustion is. Here, are any equations given, Raima? No, they aren't, are they? And frankly speaking, this is the only thing that is tested. Otherwise, you need to know. Sir, can we deal like this formation? Abdul Muiz, just wait a second. Your question is very beautiful, but wait a second. For now, no. Yeah. What is the answer, guys? Can you guys not give me the answer and just give me the answer. Give me the answer. What's the answer? Minus 575 kilojoule per mole. And for MCQ's sake, This is what your teachers would have taught you. A lot of teachers would have taught you this. See, what is this? This is X. This is the enthalpy change of reaction, isn't it? X plus this is the enthalpy change of combustion of products. So X plus the enthalpy change of combustion of products is equal to the enthalpy change of combustion of reactants. So you guys can remember or learn the equation for it if you want. But it's slightly different, slightly different. So enthalpy change of reaction plus enthalpy change of products. Enthalpy change, which enthalpy change? Enthalpy change of combustion of products equals the enthalpy change of, you see, this plus this equals this. Enthalpy change of combustion of reactants. Happy? So this is an equation which can be tested in the MCQs that, hey, what is the enthalpy change of combustion? How can you calculate it? This is how I'm calculating it. Sir, why aren't you opening all chat? Here you go. You guys can chat. Hamza, if you want to make friends, you can. Have it done? Acha. That's the idea. That is the idea. And if you want, I can show you pictures. I can show you pictures. I want to show you pictures and pictures and pictures. I think this is a good picture. This is a good picture. Where is the pictures? Yes, it's in there. It's in there. See, that's it. Please understand. See, your books has it written like this. Remember, always remember, and I want to do it right here as well. Always remember that if you were to go against the arrow, you would change the sign. Please always remember this, right? So I like to go as the arrow flows. So it's like whoop and whoop, whoop equals whoop, whoop equals whoop, right? But if you want to go against the arrow and you want to say, hey, I want to land here. I just want to land here, right? I want to land here. So this would be what? This would be X equals, and then you'd go, this would be your direct route. And then this would be your indirect route. Isn't this true? Sorry for my drawing, but this would be your direct route, and then this would be your indirect route. Now see, after you go here, this is what? X equals minus 2509 plus, please, it's a law of heat summation, plus minus 286 plus, now this is very crucial, very crucial. See, it's plus here, but as you're going against the arrow, this minus becomes positive, right? Because now you're going against the arrow. So enthalpy change of combustion for this fella was minus 2220. But if you wanted to go like this, that this is X, and you wanted to take this route, and you're going like this, hey, this is, you're going with the flow of the arrow. But now all of a sudden, when you go up, you're going against the arrow. So if you're going on the, if you're not going like this, you're going opposite to the arrow, then this enthalpy change becomes positive. Just like when you were studying reversible reactions, the forward would used to be exo, so the backward would be endo. The backward would be exo, so the forward would be endo, right? So this is how it used to work. So similarly, please do not put any sign on your own. It's negative plus this plus, now this sign is going to change. So it's this plus 2220, and you're going to get the same answer. You're going to literally get the same answer of minus 575 kilojoule per mole. So it's up to you which route you want to take, and this route has been taken by your book. See, he's saying, hey, you go like this, and then you whoop like this, you go like this, whoop, like this. So if you say, hey, this is X, this is Y, let's suppose you say this is X, this is Y, and this is Z, so then this would be X equals, I want to end here, right? So if this is my direct route, this would be my indirect route. So X equals Y plus, and then now you're going against Z, so it would be minus Z. So X equals Y minus Z. This is how it would look like, right? So this is how your book has talked about it. Okay. Anyone wanna make friends? Kill yourself. Dettol ki bottle le aap pee le. Right? And let me show you guys some other things that your book has said. Other things. Not your book. These are multiple books. About 20 books. This is not what your book has said. This is what 20 books has said. See, this is how they've even proven it. This is how they've even proven stuff. He's saying, hey, I want to start here and I want to end here, just like me. So in this case, he's done it like me. He's saying, whoop, whoop. You're going like this, H1 plus H4 equals H3 plus H2. That's how you're going here, right? Just like me. Here, he's following me. Here, he's defying me. But both would give you the same answer. Just remember, if you go against the arrow, the enthalpy change sign changes, not the summation signs, right? And see, the book had very good, very beautiful thing to say when I took the snippet from it. Look at what it's saying. It's saying, hey, it's saying take care. See, he's written the equation like this, but I like to write it the way I've written it because it's so logical. You can then mingle with this, right? So if you can write it like this, you can mingle with this. The examiner has written it from the perspective of enthalpy change of reaction. So this would be equal to, you'll take this and it'll be subtracting on the right hand side. So this would be equal to enthalpy change of combustion of reactants minus enthalpy change of combustion of products. And right here, the examiner has, done it like so. And this is for, this is for the formation. He's done it for formation. It's for formation. For formation, it's products minus reactants. For combustion, it's reactants minus products, right? So the examiner has said, and the book author has said something beautiful, which I always say. What has he said? Please read this out loud in your homes. If you're sitting in your home, read this out loud. He's saying, take care. Enthalpy changes for reactions can be calculated from enthalpy changes of combustion. The relationship then is sum of reactants minus sum of enthalpy change of combustion of product. So do not rote learn these formulas in a parrot fashion. Don't be a rote learner. Check with the Hess cycle each time. So I follow the guidance of these awesome authors who teach students and also teach teachers to not teach the formulas. So beautiful. He's saying let the students derive them on their own. If they know the Hess cycle, they can derive the formula on their own. And just like I've never rote learned the formula. I always derive it. See, I've derived it in front of you. X plus this equals this. That's it. So see, enthalpy change of reaction equals enthalpy change of combustion of reactants minus enthalpy change of combustion of products. And this is how he's written it. Minus sum of the enthalpy change of combustion. He's writing sum because there can be many reactants, many products, right? And that's the idea. Maza aaya? So even the examiner is against, and the author of the book is against rote learning formulas. Right? Now, another question. Let's suppose you had carbon solid and hydrogen, and you wanted to, it goes into C2H6, right? It goes into C2H6, and this is 3 and this is 2 right here. And I want to figure out the enthalpy change of reaction right here. What's the enthalpy change of reaction? Now, remember, in your exam, whenever you are given data, think whether you can use formation or whether you can use combustion. Is it formation data? Is it combustion data? And can I use them? If neither succeeds, if you do not succeed in using, you cannot use neither information. It's not neither the formation data is given to you nor the combustion data is given you. Then stick to the method that I taught you at the start of the classes. Right? But please understand, I've not given any data yet, Raima. It is formation of this, but I've not given any data. The reason why I'm saying this is because before I test you guys on this, I want to test you guys on something else. Please, I want to test you guys on something else. You have C3H6 plus H2 and gives me C3H8. Right? The same example that I want to do again. I want to do this example again because I want to make sure to confuse you guys. This is C3H6 plus O2 giving me it's giving me CO2 plus H2O, and this is like 3. Can I use the equations above? Wait, please. Okay, don't cheat. Close your eyes. Don't cheat. Don't cheat. I want to make my life easy by just using these equations. बेटा मेरा ज़हनी तवाज़ुन हिला है. That's why I'm making these noises. बस खुश हो गया हो. तब अल्लाह सबको खुश रखे अपने खर्चे पे. वाह, ये क्या कॉपी हो गया? सिर्फ इतना कॉपी हो गया. मनहूस. Sorry guys. Sorry everybody. जी बिल्कुल मैं पागल हूँ. मजाक कर रहा हूँ यार, मैं कोई पागल नहीं. किसी ने भी ये नहीं कहा. मैं अपने आप से बात नहीं कर रहा. I'm talking to myself. the enthalpy change here is minus 2509. The enthalpy change here is minus 2220. The enthalpy change here is, sorry, here it's minus 2220, and here it's minus 286. So the examiner started to figure out that students have rote learned stuff. And so he started testing like this. He gave you the equations instead of giving you guys data, right? But after you look at the equation, you can decipher something. What can you decipher from this? You can decipher that, hey, hold up. This is combustion data that's been given to me, right? This is combustion data. And I'll tell you that it's combustion data. I'm sorry. I'll even tell you that these are all combustion data, right? So I'll even tell you this. But instead of giving it to you guys in the form of letters and alphabet, examiner realized that students have just rote learned. Whenever they see the C sign, they put up 3 brackets and put combustion products. So he started giving this equation. And if I look at my equation, I will always first think to myself, is this combustion data? Is this formation? Can I solve it through formation? If yes, then okay, solve it through formation. If I can I solve it through combustion? If yes, then solve it through combustion. And if you fail in both, then move on to my method. Now here you're given 4 big ass equations, right? But can I solve this through combustion data? Absolutely I can, because I realized that, hey, he's given me combustion data and it's for this, this, and this. So it's basically, effectively, it's the enthalpy change of combustion for C3H6 right here. This is the enthalpy change of combustion for H2. This is the enthalpy change of combustion for C3H8. He's given it to me right here. And then you realize, hey, it's the same boring old question and you could solve it, right? So this is how the examiner can play his game. Now here, I want to test you guys again. And see how good your concepts are, right? Now, if the examiner gives me combustion data, what do you mean balance khud karni hai? Yes, obviously, Abdul Muiz, he's gonna give you balanced equation, but if not, then balance it. It's not rocket science, is it? It's good stuff. Sir, I always get confused on whether positive is endo or is exo. How do you learn it? Aliza, endothermic. Endo is derived from a Greek word called inside. Endo means inside. Inside out. Inside is positive. Hey, happy. That's how you can remember. Exo means exit. Exit means, oh, happiness is exiting, negative. Here you go. You can remember it like this. If you can't remember these things, it's okay. Make acronyms for yourself. Like it's basic stuff. If the examiner Raima, then it becomes a little complicated and examiner will not test such questions. Even the examples that I did at the start of the class, they were pretty technical and rarely tested. This is what's mostly tested. Happy? Chalo, let's do this. Now, if the examiner gives me, very good question. Sir, if data is mixed combustion and formation, Abdul Muiz, this is what I was coming to. So the examiner, and these 3 are largely what the examiner tests normally. So if the examiner gives me combustion data, how do I solve this? Plus, solve it with the X's and Y's, If you're done, right? So this is combustion products. Now I'll see your concept. See, how do I solve it? Sir, this will undergo combustion. Please, it's combustion, not formation. Formation for this would be 0. But combustion, it's undergoing combustion, right? So what would it be? The enthalpy change of combustion of graphite. And this should be multiplied with what? Should it not be multiplied with something, or should you take it as it is? Should you take it as is, or should you multiply it with something? I should obviously multiply it with 2, because enthalpy change of combustion for graphite is for 1 carbon. It's for 1 carbon. This you need to multiply it by 2. Similarly here, enthalpy change of combustion of hydrogen. But you have 3 moles of hydrogen. Combustion is for 1 mole of the substance which is burnt. This you have 3 moles, so times it by 3. Here, it's enthalpy change of combustion of C2H6, and it's 1 mole, so it's just the same. See, that's how easy it is, and the examiner can actually make you calculate it in this perspective. So he might give you in MCQs which is the correct option, and the correct option should be what? The indirect route equals the direct route, right? So it should be enthalpy change of reaction plus enthalpy change of combustion of C2H6 equals enthalpy change of combustion. See, it's so fun now, of carbon into 2 plus enthalpy change. See, and this looks so complicated, but if you know your Hess cycle, it's a piece of cake, isn't it? It's a piece of cake, isn't it? This would be the correct MCQ then. And these things can be tested in MCQ and widely tested in MCQs, right? So this is if the combustion data was given to me. I'll take the same equation now. I'll take the same equation. 3H2 gives me C2H6. And now the combustion data is not given to me. Formation data is given to me. How do I use it? Well, I know formation data mein 1 mole of a substance is formed, right? So formation data. Please, why am I writing formation data here? Right? Elements here, right? Elements will make up these reactants and products. Sir, please do not be confused with this 2 and with this 3. These are elements. Elements formation is 0. It's like saying 0 equals 0. It's like saying if you have 2 carbon solids being made, they're going to be made from 2 carbon solids. It's like saying 2 equals 2, 1 equals 1, right? Similarly, so enthalpy change of formation for any element is 0. It's a null reaction, and I've explained it in the first class in a lot of detail. Not in the class I taught yesterday, but in my live class, right? Similarly here, what's the enthalpy? What am I going to do here? This would be enthalpy change of formation of C2H6. And because 1 mole is forming, I don't have to do anything. So how would you actually write it for the examiner? It's going to be what? The indirect route whoop, equals the direct route. Whoop. So 0 plus x equals the direct route. So x would effectively be a 0 plus x. X is what? The enthalpy change of reaction. And this would be equal to the enthalpy change of formation of C2H6. And you'll realize that enthalpy change of reaction and formation can be equal. See, enthalpy change of reaction is equal to the enthalpy change of formation of 1 mole of C2H6. So this is how you'd go about it. Now, this is where things get fun, right? And before they get fun, because not all of you have taken my live class, the first class which I taught, because it wasn't open for everybody. But before I teach you guys the third thing, can you guys tell me, magnesium plus oxygen gives me MgO, hydrogen plus oxygen gives me H2O, you know, and similarly like N2, oh, not N2, let's use something else. Magnesium ho gaya, hydrogen, carbon plus oxygen gives me carbon dioxide, right? And let's balance this out. So this is half here, and nothing here, right? Can I say that these are being combusted? Magnesium, hydrogen, and carbon, they are being combusted. So now can I say that this is the enthalpy change of combustion of magnesium? Can I say this is the enthalpy change of combustion of like hydrogen? Yes. Can I say this is the enthalpy change of combustion of like carbon, graphite effectively? Yes, I can say this. But something else, 1 mole of something else is forming. Boop, boop, boop. 1 mole of MgO is forming. So can I say enthalpy change of formation of MgO? You can also call this enthalpy change of formation of MgO. Enthalpy change of formation of H2O liquid. You can call this the enthalpy change of formation of what? Carbon dioxide. So 1 mole of a substance forming, right? So effectively enthalpy change of combustion for elements, enthalpy change of combustion for magnesium would be equal to the enthalpy change of formation of MgO. You could say this, you could say this, it doesn't really make a difference. So whenever you have elements, this is very important. Whenever you have elements being combusted, the elements, if elements are being combusted, you know, the enthalpy change of their combustion would be usually equal to the enthalpy change of their formation, of the formation of their oxide, of the formation of their oxide, of the formation of their oxide, right? So that's the idea which I taught in the first class, in the last 10 minutes of the first class effectively. Now, I want to mix you guys up. What I'm going to do is I'm going to give you the same equation, and this is the last bit to it. Then bond enthalpy and all of that, enthalpy change of atomization will be left. I'll teach that some other day, maybe on Thursday. This is C2H6 which forms, and this is 3. Now, Moiz asked such a beautiful question, and that is also widely tested in the exams. Sir, if 2 moles are products are being formed, so we divide the equation for one. No. We don't do that, Abdul Muiz, because in enthalpy change of formation, 2 moles wouldn't be forming. Enthalpy change formation is for 1 mole forming, 1 mole forming, 1 mole forming. When you write equations, you write them correctly, not when the examiner gives you equations. Now, examiner can give you any sort of equation, right? But when you write the enthalpy change of formation, for this you need to watch the first lecture. If you want to write the enthalpy change of formation of MgO, it must be 1. It can't be 2, right? It can't be 2, can it? Yes, if you are saying this, then you are right. If you're saying, hey, if it's N2 plus O2 giving you NO2, right? And let's suppose this is half, and this is like half. Sorry, NO2 is not half. Let's make this NO. Right? So now you could say, hey, 1 mole of NO is forming, so I can say this is the enthalpy change of formation of NO, right, Abdul Muiz? And here nitrogen is being combusted. So enthalpy change of combustion of nitrogen is this, but see, it's not the enthalpy change of combustion of nitrogen, is it? What is it? Enthalpy change of combustion of nitrogen should be of 1 mole of nitrogen. You have half. So this is also half enthalpy change of combustion for nitrogen, and this is equal to the enthalpy change of formation of NO. So if you're saying this, then you are right. And if you're saying something else, I don't know what you're saying. If you're saying this, then you're right. But these things are rarely tested. Next, so now I'm gonna throw a curveball at you. Examiner figured out that students have now started to rote learn things. If you give them combustion data, they make combustion in the intermediate stage, and then they just point arrows at it and do indirect state equals direct state, blah blah blah. If you give them element stage, they just make elements in the intermediate box, and then they put arrows towards the reactants and towards the products and just write the answers, right? The examiner says, wait, let me throw a curveball at them. बड़े मस्त हो रहे हैं, बड़ी free हो रहे हैं. Let me throw a curveball at them. And what he did was something very beautiful. What he did was, he said, wait a moment. I'm gonna, like Abdul Muiz said, I'm gonna give you formation data, and I'm gonna give you formation data, and I'm gonna give you combustion data. Up करके दिखाओ. He was like, up karke dikhao. C2H6. Now students were bamboozled. All the students on the face of planet Earth were now bamboozled. They were like, oh my God, kill me please. 95.5. This is about minus like 286 kilojoule per mole. And this is about minus 1560 kilojoule per mole. And here is where the idea of equations come into play. So before I solve this, I'm given formation data, I'm given combustion data, right? I'm given formation, and combustion. Now I can do two things. And it depends on how strong your intuition is, and it depends on your practice, to be honest. But I'm going to teach you both the methods, and then when you practice, it'll automatically click. You'll be like, okay, this can work, that can work, it's all good, everything can work. And before you can directly do it, I want you guys to open up these equations. So what is the enthalpy change of formation of carbon dioxide? How does carbon dioxide form? Formation. How does it form? It forms from its elements in its standard state. So this is graphite and this is oxygen, doesn't it? So that's the enthalpy change of formation of carbon dioxide. I'm just writing the equation for you guys, the ones that the examiner has given me, right? And similarly for enthalpy change of formation of H2O, which means H2O is forming. How should it be forming? From its elements in its standard state, hydrogen element and oxygen element, right here. Gas and gas, and that is what, half O2, right? And this is the enthalpy change of formation data that he's given to me. And just like Abdul Muiz said, hey sir, combustion is now given, how are you going to do this? Combustion data is what? When 1 mole of this combusts, 1 mole of C2H6 burns in oxygen, gives me carbon dioxide and water, right? And now see, this is so beautiful. Okay? This, I don't know. And this I know, let's balance it out first. You have 6 H's here, I'll put a 3 here, and then you have 2 plus 3, that's 5, so this is 5 over 2, right? 5 over 2, what the hell? First balance out carbon, Suleiman, what you doing? 2 carbons, now this is 3 plus 4, 7, this is 7 over 2, not 5 over 2, Suleiman. What the hell, right? And we need to find this fella. We need to find this stuff right here. Now, this becomes a little complicated, right? Sir, how in the world can we figure this out? For that, you'll have to use your brain. You're given combustion data for this, aren't you? You're given combustion data for this. Can formation data be given to you? Can formation data be given to you for this particular equation? No. You can't, because formation, this doesn't even fall under the category of formation. Formation for this is impossible because formation requires elements. This is literally a molecule which is making up this. So you can't use formation. So you're given combustion data and then you're given formation data. But for this, you can never ever use formation because this can never be converted into a formation equation. Since this is a molecule, formation क्या होता है? What is formation, everybody? If I want to form C6H12O6, I would form it from its elements. Please, in its standard states. Please understand this, very important. There can never be a molecule, there can never be like a compound written here. I won't say the word molecule, but a compound. A compound can never appear in a formation equation on the left-hand side as your reactants. Nah. So how do you convert this? You don't. So I am now stuck. I'm stuck. I'm given combustion data and then I'm given formation data. I can't convert this into formation. But if I look at my formations, I'm like, wait a moment, something fishy is happening. I'm given formation data of carbon dioxide, but that is also equal to the combustion of carbon. So this is effectively delta H formation equals delta H combustion of carbon. Isn't that true? Similarly here, delta H formation of H2O is equal to what? Delta H formation of delta H combustion of hydrogen. And effectively, the data that has been given to me, now I will focus on this. I'll turn a blind eye to it. I'll be like, hey, stop trying to confuse me. Delta H formation of carbon dioxide is effectively delta H combustion for carbon. So both the values are equal. So effectively what I'm given, I am now given combustion data. This is combustion, that's combustion, that's combustion. And so if combustion data is given to me, it's a piece of cake for me now. This is the equation. Carbon, hydrogen, and C2H6. So I'm gonna put my 3 blocks here. I'm gonna put combustion products, carbon plus hydrogen gives me C2H6, and that's the last thing which is tested. This is 2, this is 3, this is X, I don't know, but see, now I'm given combustion data for carbon. What is the combustion data for carbon? It's the same as formation for carbon dioxide right here. And what is that? That is equal to minus 395.5, minus 395.5, right? Similarly, combustion data for hydrogen, that's also given. You might think it's not given, but it's given. Formation of H2 is effectively the combustion of hydrogen, which is given to me, which is what? Minus 286. Minus 286, right? And similarly here, combustion for C2H6 is equal to, it's already given. It's not equal to anything, it's given. Minus 1560. Minus 1560, right? And so what does that give me? So the direct root equals the indirect root, right? So X, or the indirect root, equals the direct root. I couldn't care less. X plus minus 1560 equals minus 359. But please understand, see, here you have two carbons, 2 moles. Combustion is for 1 carbon. This is 2. So please do not make this mistake like I did. Multiply this by 2, multiply this by 3, please. Because see, it's for combustion of hydrogen, it's for 1 mole of hydrogen. Here you have 3, right? So please do not make this mistake. So it's this 0.5 multiplied by 2 plus 2 minus 286 times by 3. And what would that give me, sir? Aren't we going against the arrow? No, we're not. I'm going like this, see? So X plus minus 1560 equals this. I'm going like this. I'm not going like this and this. No, I'm not going against the arrow. I'm going like whoop and then whoop. Right? Abdul Muiz, see, it's X plus this equals this. That's how I'm going. I'm not going like this. I'm not going like this and this. If I were to do this, then it would be X equal to all of this plus, and then this would also be a plus. So all of the X equal to all of this, a plus, and plus 1560. Then you would be going against the arrow, right? So it's pretty basic. I'll also do it for you in this white thing. First, let's complete this. What do you get here? What do you get here? Minus 86 kilojoule per mole. And if you want me, Abdul Muiz, I'll also do it for you like this. You know, the white one I'm doing for Abdul Muiz. So now it would be what? X equals 2 times this right here, 2 times this plus 3 times this, right? So 2 times minus 395.5 plus minus 286 into 3 minus 286 into 3 And now plus, again, it's a law of heat summation, plus, but this minus 1560 is now going to be a positive 1560 if you're going against the arrow, right? So against the arrow, the enthalpy changes flips. So now it's positive 1560, right? And what does that give me? The same, minus 86 kilojoule per mole. So Abdul Muiz, this was for you. Love you, man. Love you too. Thanks. Love you. Isn't it like the head to tail rule we follow in vectors? Aisha, I don't know head to tail rules in vectors. I am pathetic at physics. I hate physics. Physics is the hatred of the hatred. Got it? Done? Pretty easy stuff, huh? So that is the anomaly right here. So remember, whenever combustion and formation data are given to you, always keep your eye out for this. And frankly speaking, in your exams, you're largely tested on this. That's it. Largely tested on this. There was also a very long ass method of doing this. And I don't want to go into the detail for it. It's like the one that I did at the start. You want me to go over the long ass method to do this? It's just gonna waste a lot of time. In that case, then I'd write the most populated equation in the start and end stage, and I'd say, hey, this is combusting, okay, this is. Do you want me to do it like that? If you want, I can also do it like that if you want. Right? That's the lengthier way. And if you want, I'll also do it through the lengthier way. If you want, I can also do it to the lengthier way. So the most populated equation is this fella right here. I'm going to pick this up as the start and end stage. If you want, yeah, just for you guys. C2H6 plus what? Plus 7/2O2 gives me carbon dioxide and H2O. 2CO2 plus 3H2O, right? Is that what it gives me? 2CO2 plus 3H2O, yeah. Acha. So the other way of doing the same question was also an easier way, which is from the perspective of formation, right? From the perspective of formation. Because you will realize that, hey, this was what was required, right? And what effectively is this? This is the enthalpy change of formation, right? This is the enthalpy change of formation of C2H6, right? I don't know this. I have to figure this stuff out. I don't know what the enthalpy change of formation of C2H6 is, right? So what can I do? What I can do is I will take the most populated equation right here. This is the most populated equation, and I'll write it just like I've done right here. I've written the most populated equation at the top right here, start and end, right? And I know what this is. This is what? Minus 1560 right here. Now I don't want to do all of this thinking. So what I did was I did a shortcut. I just took the most populated equation and I just plugged it in here. And I know that's the enthalpy change of combustion right here, what is given to me, right? Now, elements going into this is what I don't know. Effectively, this is what I don't know, right? See, this is what I don't know. Carbon plus hydrogen going into C2H6, the enthalpy change of formation of C2H6, this is what I do not know. And I know the enthalpy change of formation of oxygen is 0. What's the enthalpy change of formation of carbon dioxide? Right? That's given to me in the question. Where is it? The formation data. Where's the formation data? It's minus 395.5. Minus 395.5 and times it by 2. Because you have 2 carbon dioxides. And again, this enthalpy change of formation of H2O, it's 3 times. What's the enthalpy change of formation of H2O? As given to me, that's minus 286. Minus 286, right? So you could have also done it like this. See, now the indirect root equals the direct root. So you can say x minus 1560 equals, or you should have written it not like this, you should have written it like this: x plus minus 1560 equals minus 395.5 times 2 plus 3 times minus 286. And what do we get? Voila, you get the same answer, which was minus 86 kilojoule per mole. So it's up to you, but I wanted to teach you guys this version as well, because not a lot of you guys think like this. So I wanted to teach you guys this version as well, whereas this is the shortcut for it. It's not actually the longer method, it's the shorter method. Yeah. Minus 89, you guys are doing the calculations, I'm not. It's minus 89, okay. I saw somebody wrote minus 86, so I just wrote it. It's going to be the same. Is this also minus 86? 89? Then this should also be minus 89. You guys are doing calculations, guys, I'm not. So it's you guys, please. Calculator mein aap logon ko nahi sikha sakta, right? Both are -89. So that's the idea. So one thing is like, you write the most populated equation, whoop, whoop, and then you think from the perspective of elements. Hey, elements formation data is given for me for this, formation is this is not given, this is 0, and this is what was not given. See, this was effectively the formation of C2H6. So you could do the direct, the shorter version for it. In the exams, I'd prefer you guys sticking to this trick, which is write the most populated equation and tuk, right, from the perspective of formation. Or you could have done it like this. Both give you the same idea, but I wanted to open your brains to this idea. Maza aa raha hai? Sir, why was O2 0? Maz, conceptual error, kiddo. Delta H formation for elements is 0. It's a null reaction. For elements, formation data is 0. And I've gone over this multiple times. And even during the class, I've said this a lot of times. And the reasons I've given in my live classes, I don't want to go into the detail for it. The why, sorry, kiddo, it's going to take a lot of time. Okay, why is it a null reaction? I just told you it's like 2 equals 2, right? But more detail has already been given. For now, just focus on solving questions. Now, one more thing, which is written in all books, but has been only tested once, which is what if you wanted to figure out the enthalpy change. It's written in every book and under the AS chemistry section. So what if there's enthalpy change of hydrated salt? How do you figure this out? Now, this is in a lot more detail in your A2 level, but for now, I'll just go over the one example which is given in every single book, be it Pearson at Excel, be it AQA, be it IB, be it Cambridge, be it all the 4 books of Cambridge, be it the 3 books of IB. I went over every book, and in every book, the same example is given under the AS level section. So just to be on the safe side, I want to also teach that. I won't give you guys more explanations to it, but I'm going to teach it to you. See, MgSO4 plus H2O, just like 7H2O, and this gives me MgSO4 dot 7H2O, right? And this is what I'm going to figure out. This is a solid, this is H2O liquid, this is basically a solid hydrated salt, right? Now, this is very simple, very simple. And after this, atomization is going to be left and bond enthalpy. We're going to do that some other day, but this is the last thing which I want to do. Now, what the examiner would do is he would give you the enthalpy change of solution for MgSO4 and the enthalpy change of solution for the hydrated salt as well, MgSO4 dot 7H2O, right? Because when a solid dissolves in water, that's basically enthalpy change of solution, right? So here you basically have aqueous, AQ, what's the spelling of aqueous? I'll just write AQ. I know the spelling of aqueous, okay? Please, okay? So this is MgSO4 aqueous effectively, right? MgSO4 aqueous. But I'm just going to write aqueous ions, right? So what am I going to do? In solid, MgSO4 solid to MgSO4 aqueous, that's basically what that's given to me. It's about minus 91.2 kilojoule per mole, and this is about plus 9.6 kilojoule per mole. So if I want to figure out X, this will be minus 91.2 kilojoule per mole. For water, it's just water. It doesn't have any enthalpy change of solution. Enthalpy change of solution is for this fella right here. And this enthalpy change of solution is going to be what? Plus 9.60, and the idea is the same. Direct root or equals the indirect root, or direct root is the blue. So direct root equals the indirect root, however you want to do it. So minus 191.2 equals X plus 9.60. And then X equals minus 91.2. This goes there. Minus 9.60. X equals, what do we get? And this is largely part of A2. This is basically called enthalpy change of hydration, which is not a part of our course. No, you study this in A2, but I'm just putting it as X. What do you get? Minus 99.8. That's it. Kilojoule per mole. And this is the only example given in all the books under the AS section. So that's why I wanted to go over this. That's it. Sorry, it's 100.8. Whatever it is, yaar. It's 100.8. Happy? But that's it. That's basically, you just write the solution. This also dissolves, and tuck. Indirect equals direct. That's it. One last idea, if you want, it's called algebraic manipulation. again, algebraic manipulation. See, at the end, I always teach you guys some extra things which obviously you might not require, but it's good to know. Algebraic manipulation. For example, and I just do one example for these two because this algebraic manipulation is given in one. Sir, how is this hydrated solid in the form of crystal? Come on, Raima. Copper sulfate .5H2O is blue crystals. Hydrated salts are always in the form of solids. So algebraic manipulation. And this looks like something like this. So mathematically, without the Hess's law or the Hess's cycle, not without the Hess's law, but without the Hess cycle diagram, you can solve this mathematically. And I'm going to do this one example and nothing else. So, and here I have like carbon monoxide plus O3. And we never really do this for complicated questions. We always use the Hess's law, right? Or the Hess cycle. And this is 3 here, and that's about 3 here. And I think that's good stuff, right? That's good. That's carbon dioxide into carbon monoxide plus oxygen. And then you have like this, and then you have 3, then you have O2 going into O3. And what I want you guys to do is, I want you guys to figure out the enthalpy change of formation of O3, of ozone, right here. O3 is ozone. Now, please, I have not given you data for the Hess cycle. Hess cycle data is not available. And this is just algebraic manipulation. I'm just going to say, hey, this enthalpy change is plus 566. This enthalpy change is about minus 992, right? I've not given you guys Hess cycle data. This is data which you can do algebraically. Yeah? And this question is designed in such a way which compels you to do it algebraically. Okay. Now, how do you do it algebraically? Basically, you manipulate the equations. You manipulate the equation so it looks something like this. See, if you want to figure out the enthalpy change of formation of O3, it should look like something like this. Where is oxygen? Oxygen is in this equation right here. So I'm going to manipulate this equation so that this oxygen is on the left hand side and it is 3/2'd, right? So what I'm going to do is I'm going to first flip the equation, right? This is algebraic manipulation, not a part of your course. Please, those who don't like math, those who don't appreciate math, skip it, please. Don't even look at it. So see how I'm going to manipulate the equation. Oxygen plus 2 carbon monoxide gives me 2CO2, doesn't it? And so now the enthalpy change should be minus, I flipped it, so it should be minus 566. And frankly speaking, I don't need O2, I need 3/2 O2. So what I'm going to do is I'm going to multiply this entire equation with 3/2. And so this would also be multiplied with 3/2. And I'm going to get what? 3/2 oxygen plus 3/2 multiplied by 2 carbon monoxide, that gives me 3CO, gives me 3CO2, right? 2 multiplied by 3/2, right? So this is what I've done. And so what is my enthalpy change now? If you multiply something with 3/2, this should also be multiplied with 3/2. What should be my enthalpy change? So it should be minus 849. Thank you. This is the manipulated equation. Okay? H side to aa gayi. Ab on the right side, what I need is I need this ozone. I need O3 to be on the right side. So what I'm going to do is I'm going to flip this. So I'm going to say, hey, you had 3 carbon dioxide on the left now, and you have 3 carbon monoxide on the right and O3. But now the enthalpy change, see, I've just flipped this. The same equation, I've just flipped this. This goes there, but now the equation, the enthalpy change is positive 992. Positive 992, right? Because you flipped it. And now add the equation. Because now I have this on the left and this on the right. If you add the equation, this cuts out with this cuts out with this, and you end up with 3/2 O2 giving me O3. How? You just added the equation. So minus 849 was added to 992. And this is called algebraic manipulation, not a part of your course. I repeat, not a part of your course. I repeat a 50th time because I know after near the end of the exams, students will start saying, "Sir, is algebraic manipulation?" Okay, please, it's not. It's something really cute. I wanted to teach it to you guys. Those who appreciate math would also have appreciated this. If you don't appreciate math, if you don't like math, it's okay. It's okay. Skip it out. Don't really care, right? Yes, if you wanted to do this through Hess cycle, then enthalpy change of formation data should have been given to you. Yes, you're right. And so the only part which is left is now bond enthalpies and enthalpy change of atomization and vaporization. I'll do that on Thursday and we'll be done with this chapter. So this was so cool. I'm happy, Hasib, that it was cool. I'm happy. So this is a technique called algebraic manipulation, but you never really use it. We always use Hess cycle because this only works, in if your math is really good, you can make it work for every single equation, but it would take a hell lot of time. So I would always recommend to not use math and use Hess cycle. Although this would work for every equation, but we normally use it on simple equations because it's just easy math. If you started to use it for this equation right here, you could have done so. For every question that we've studied, we could have also done algebraic manipulation for it. But see, it's not part of your course and it would take a hell lot of time, right? So that's it. That's it for today, guys.